so much for checking out the Weaviate podcast. We've had a lot of great guests in the Weaviate podcast, but I'm super excited about our next guest. We have Jonathan Frankle from MosaicML. Jonathan is one of my favorite research scientists in deep learning to follow along with. Since the debut of his paper alongside Michael Carbon, his advisor at MIT, the lottery ticket hypothesis. This paper won an ICLR best paper, and it was just an incredible finding about the ability to apply these sparse mass onto these subnetworks, and this kind of idea of pruning and how you can kind of achieve this training of the sparse subnetwork from scratch is theoretically possible. And now Jonathan has continued this research, developing all sorts of things related to efficiency and efficient deep learning algorithms, exploring the benefits of things like masking with pruning and all these kinds of things that Jonathan will explain to you better than I will in this quick intro. But I'm so excited to learn more about Jonathan's latest company, MosaicML, and the product Composer. And for our Weaviate community, this is super interesting because, they're making it more efficient, faster, cheaper to train models. And then we get our vector embeddings that we can search through for semantic similarity and all sorts of things. So, Jonathan, thank you so much for coming on the Weaviate podcast. And can you tell us about MosaicML and maybe what I've botched in my quick intro?
No, this is great. So the story of MosaicML goes back almost 2 years now. And really, it started with an email from our now CEO, Naveen Rao, to me and my advisor saying, hey, nice lottery ticket paper. Want to do a startup based on that? And my first reaction, anybody's reaction who knows the lottery ticket paper well, should be, are you insane? Interesting science, not useful. And, I'm willing to admit that, this work is not practically useful. It was meant to be an exploration into understanding deep learning. But in order to use lottery ticket practically, you would need two things to be true. Number one is you need some magic way to find sparse networks early in training. The work is all about showing that these sparse networks exist, but it doesn't show an efficient way to find them. And people have been working on this problem in the literature, but in my mind, there hasn't been a ton of progress, to be completely honest. And I can say more about my thoughts on that in a moment. The other piece is that suppose you found one of these subnetworks, you need to train efficiently when you have a sparse network. And, for those who aren't familiar, just because a network has fewer parameters doesn't mean it trains faster. The network will hypothetically require fewer calculations, fewer floating point operations to be able to train. But that doesn't make it go fast because our hardware can't actually take advantage of the topology of the network. GPUs and modern TPUs and hardware like that can't take advantage of sparsity very effectively. It's used to processing, contiguous matrices or tensors or vectors. So I kind of looked at this email, getting back to the topic, I looked at this email from Naveen and went, is he nuts? This is a pretty smart guy. But we got to talking, my advisor and I sat down and talked to him, and, Hanlin Tang, his colleague from his Nirvana days, also joined, now our CTO. And we came to the following conclusion. There's a lot of opportunity to improve neural network training by making the training algorithm more efficient. And what I mean by algorithm is the following, because it's worth clarifying here. So there are a lot of ways that you can make training more efficient. One is you can build a faster chip. Like NVIDIA just released the H100. It's a lot faster than the A100, which is a lot faster than the V100. That makes training more efficient and cheaper. Another thing you can do is write better compilers. You can take the same set of operations and run them more efficiently. These are things like CUDNN and kernels and Triton and that sort of thing. But I think the interesting observation here is all of this is taking the exact same math, the exact same way of training, every operation that you're doing, and just finding ways to run it faster. You can, spin the GPU faster. You can have, faster tensor cores. You can, pick the right operations to run it faster, but it's still the same math. You'll get exactly the same weights in the network, assuming, non-determinism doesn't kick in on the GPU or things like that. And the lottery ticket work is interesting because it says, actually, we can change the math. We can get you a different network than you would have gotten otherwise, but it's just as good. And hypothetically, in our fantasy land where we can accelerate sparsity, it would have been more efficient to get there. We can change the algorithm to make it more efficient. And that's what Mosaic is built on, is trying to look at ways that change the math, that fundamentally change the training algorithm to make things more efficient. And I'll give you two reasons why this, makes a lot of sense to me intuitively. One is that, think about the math behind deep learning. There's nothing correct about this. It's not like we're doing the right thing and Mosaic is doing the wrong thing, but making it work. We're using SGD, which is a convex optimization strategy in a non-convex landscape. If you want to get that network to train, you need all the right hyperparameters just the right way. If you set the learning rate a little bit too high or low, bad performance. You need batch norm or layer norm or pick your norm. You just we're living in this tiny, tiny space of networks that work well. It's minuscule. It's like, you step off of this tiny little island of stability and you fall into lava and your network doesn't work very well. So, there's nothing correct about what we're doing, so we shouldn't be afraid of changing the math. The other reason why I think this makes sense is look at this tiny space of networks. We don't know how to describe this tiny space theoretically. I can't give you a proof or a statement or a set of assumptions to describe it. And I think of this kind of, the analogy I like to use is biology. So imagine we have the laws of physics. Think of that as all the neural networks that are out there. We could describe them all. Think about biology in, the real world. This is one emergent property of physics. We are just physics. This is one outcome of the laws of physics. If I gave you the laws of physics, you would never predict the biology here on Earth, partially because it's one very small possibility in the range of a huge number of possibilities, partially because it's so complex that from first principles it would be hard to predict. I look at the neural networks we train in practice kind of metaphorically like this biology. These are highly complex systems that have emerged from very simple dynamics like physics, but it's one specific thing that might have emerged. And we can imagine all sorts of possibilities. In theory, we have to contend with all these. But in practice, we only deal with a tiny portion of them. And when we study biology, we don't go down to the physics immediately. We look at motifs and systems and behaviors and mechanisms and all these higher level abstractions, things that we wouldn't necessarily think of from first principles in physics. And so I think of this in the same way as deep learning. I don't care what might happen. I don't care what you can prove. I care about what is happening and how to describe it. Even if the descriptions aren't perfect, I don't need a proof. I just need good empiricism. And then you can think of what we're doing as almost like pharmaceuticals. We're designing some kind of chemical or some kind of intervention that takes advantage of processes we understand to get a different behavior out of the system. And so we design a lot of these interventions. Lottery ticket is one of those. Your body chemistry is no longer functioning the way it was before, but ideally you'll get to a similar place, or you'll be, just as healthy as you were before. But, ideally we can make that outcome happen in some desirable way. And, I'll continue this metaphor for one more moment. One of the big challenges is not just, designing one pharmaceutical. You need a lot of pharmaceuticals to treat different conditions or to address different aspects. And, lottery ticket you can think of as one pharmaceutical. At Mosaic, we have, I think 25 and counting right now. And that and counting is because we've got a lot more in the pipeline that you'll expect shortly. And the last thing I'll say here is if I handed you 25 pharmaceuticals, you wouldn't take them all. You wouldn't just pop all the pills into your mouth and say, I will be better now. These drugs can interact in really dangerous ways. And so a lot of the magic of our work is trying to understand the science of how do these things interact, what's going on under the hood in these networks that causes things to interact negatively. Some of this is systems optimization. Some of this is, just two methods seem to over-regularize or what have you. But there's a science here that we're starting to uncover, and that helps us build recipes. So I'll stop there. I'm rambling. But really, Mosaic, improving training algorithmically, I think this is a new layer of the stack. And I think this composes really nicely with what lots of other folks are doing at other layers of the stack, hardware, compilers, all the way up to good, UX and ML ops. So, that's where we are.
Wow, this is absolutely fascinating. And firstly, to preface this, I hope that story of the email ends up in these startup books one day. I get that idea that you get an email and that's the start of MosaicML. That should be one of those books. But I'd love the 25 and counting, the composer, the interaction effects of things like ghost batch normalization, stochastic depth, and maybe the augmix data augmentation strategy. So before coming back later on, I think I'd love to dive more into the design of Composer and its kind of API and how it integrates into most of the existing workflows of people working with deep learning. But I think it would be great to transition right now into some of the methods of Composer. And you mentioned the interaction effects of these methods, and the new science is just absolutely mind-blowing. It's such a fascinating thing. But so could we kind of come through this list a little bit, and maybe could we start off with so I kind of, as I went through the early documentation on the methodology in the Composer, I kind of chunked it up into categories of data augmentation, normalization, what I call model augmentation, and then label augmentation and optimization. So maybe let me start off with model augmentation, in which I grouped things like SWA, running average of the model weights, stochastic depth, replaces specific layer with a stochastic version that randomly drops the layer of samples during training. Can you tell me more about these kind of things like layer freezing, squeeze excite, and how these kind of things come together?
Definitely. So I think you've actually done a really good job chunking these up. I'm going to have to steal this because we're struggling with this right now. This is one of the challenges of building the science is kind of, I look at something like, let's start with stochastic depth because I think that's an interesting one. So you can think of stochastic depth as kind of a fancy version of dropout. What it does is in a residual network, you can skip a layer and the network still works. You can just kind of chop it out, but there's residual connections that route around it. So in a normal feed-forward network, if you cut out a layer, like the network's disconnected and it makes no sense. In a residual network, you can drop layers. And so the idea in stochastic depth is you can do this two ways. One is that you just, for your mini batch, you drop some of the layers and you just skip them on every forward pass. The other is that you do this example-wise. So on each example kind of takes a different journey through the network. And on each layer, you only run through some of the examples. So stochastic depth has a complicated story. On the one hand, it should hypothetically make things more efficient because you're not using the whole network on any given pass. So this should be, beneficial to speed. You might think of it as a model change in that way, but it's a regularization technique as well. So the reason why I'm picking on this one is some of these methods really defy categorization or fall into more than one category, which is what makes this science so interesting and also so difficult. And stochastic depth has an interesting story. So there are two things I'll tell you about this. One is that, the paper that came out with it makes a very compelling case that, this leads to speed up. But we actually tried it using the same methods from the paper and we didn't see any speed up. In fact, we saw worse performance. What it turns out happened was the paper had some pretty terrible baselines. They trained a CFAR10 network for hundreds of epochs. Usually, 160 epochs is enough. I think they were training for 500 epochs. In the context of that 500 epochs, the regularization really does help you and you can get better accuracy and therefore the appearance of faster training time. But, when you look at normal training regimes, this doesn't actually help at all. And in fact, we found it to be hurtful. So this is a good chance for me to take a step back and ask, what does it mean for a method to be good? What does it mean to have a positive intervention? And so here's the way we look at it at Mosaic. There are a lot of games you can play in the research literature to make something look good. One is that you can, just have a bad baseline. You can train your baseline for too long, way past the point where it's not helping your accuracy, and then show, oh, I made things faster by, showing that it doesn't take as many iterations, but the baseline didn't either. Another technique is that you can go through and say, well, hypothetically, I reduced the number of steps it took for you to reach a certain accuracy. What I'm not going to tell you is each step takes 5 times as long. And I'm pointing at the SAM paper here, the sharpness-aware minimization, where this is a huge problem. Each step takes twice as long. And you can train in fewer steps, but it slows things down. And we had to mitigate this. In the case of stochastic depth, there are two issues here. One is the baselines weren't good in the paper. The other is that just because you can drop examples doesn't mean you can get speed up from that. Going back to that sparsity example with lottery ticket, if you drop examples on each layer, you've got this weird shaped tensor. You have to reshape the tensor, run it through the layer, and then reshape it back. And that ended up slowing things down to the point where the method didn't actually help from a speed up perspective. Landon, our research scientist who worked really hard to get this method up and running, tried his darndest to find a way to get some speed out of that and struggled. But it also has a positive regularization effect. So especially for longer training runs, it is still beneficial. So these two failure modes here. One is, bad baselines. And we've seen this a lot. The other is these hypothetical fantasy land speedups, like lottery ticket is a hypothetical fantasy land speedup. At Mosaic, we care about time and cost. Those are very unforgiving metrics. Wall clock time doesn't care about flops and it doesn't care about number of steps. It just cares how long it takes to get to a certain accuracy. And so stochastic depth does help. But, I hope there are two teachable moments there for people who are thinking about this space.
So if I can unpack just a quick thing about the short and long training time, say 160 epochs to maybe test a new algorithm compared to maybe you're training the new GPT-X on your data set and you basically want to run it for as long as you can, right? How do you think about these two regimens of short and long training times?
So the way that I think about this is in terms of Pareto curves. The entire view of the world at Mosaic is about Pareto curves. Wow. So there's no right answer to the amount of training time. Really, it comes down to what is your budget and what do you care about? And maybe you don't have enough money to train GPT-3 forever. Maybe, you do. Maybe you're a big tech company and you've got a bunch of new data. You need to get a model deployed for ad recommendation as quickly as possible. So you don't have time to train it for weeks, even if you have all the GPUs in the world. And so the way that we think about this is we train the model for all different amounts of time. For any given model, our baseline is not one baseline. We take our baseline and we train it for 10 epochs and 20 epochs and 30 epochs, or we actually double, each time. But we say we don't know the right amount of time to train, so we will create a Pareto curve where we look at the trade-off between number of seconds it took or dollars it took versus accuracy. If you train for longer, generally you get higher accuracy. That's not true in general. You may eventually start overfitting or something like that. But by and large, let's just take that assumption for the moment. So you get this beautiful curve. And a speed-up method is valuable if it moves that curve up and to the left. So if it moves that curve, you get a better trade-off at all these points, or at least at many of these different number of training steps. And so you can think about a couple scenarios. Let me give you a method that takes the exact same amount of time to train, but gets you higher accuracy. Like, a regularization method, like mixup, which takes two examples and interpolates between them and then runs that through the network. Mixup doesn't really take any additional time, but it gets you better accuracy. On the one hand, that means, for the same amount of time or the same budget you were putting in, you get better accuracy. On the other hand, you could just train for less time or fewer steps and get the same accuracy you had before. Accuracy can be traded off for speed. These two quantities are interchangeable. That's really the key idea that a Pareto curve shows you. And so things that regularize and improve accuracy are speed ups for the most part. Some of them, like stochastic depth, actually, hurt you on short runs and benefit you on long runs. So there is, there's a little more nuance to it there. But, by and large, we think about this in terms of Pareto curves. And that means that bad baseline is just a point that's way far out on the right, but it's way past the point of diminishing returns. And so, it's kind of a silly point that it may not even be on the Pareto frontier as far as we're concerned, because it may be that you can train for a lot less time and get exactly the same accuracy, which means it's not on the Pareto frontier. And so we would just ignore that point as, non-relevant.
That's such an interesting way of thinking about it. And yeah, I saw a lot of Pareto curves as I was looking around the Mosaic website and getting caught up. And so yeah, I love that way of thinking about how to think about the contribution of these methods. But if we kind of step a little back into model augmentation, and you mentioned stochastic depth works for ResNets, but if you have just a sequential network where, say node A goes to B, goes to C, goes to D, and you can't drop a path because then what are you going to do? So it's kind of specific to the architectures. And then, so another thing is you've implemented Squeeze Excite, and I love SqueezeNet. All that research, the Squeeze BERT when they generalized it from computer vision to NLP as well. And there's also AliB, replace attention with AliB, and those sparse transform, all that attention stuff, obviously.
Yep.
So exciting. So how does, and before we really get into Composer and the interface and how to use it, how does that, how do those layers integrate with the way that you've defined your model code?
So the way that they integrate is we do this thing called Model Surgery, which is a module that we've written. It's part of our library, which basically allows you to do find and replace within a model graph. Wow. And this is really important for these kinds of model modifications. I want you to be able to start with standard code. I want you to start with Torch Vision or start with, HuggingFace. And then you can use our methods to replace the modules that you want. In HuggingFace, you can replace the attention blocks with alibi attention, which, doesn't cost you anything on the speed side and gets you much better, short to long sequence generalization, which means you can train on shorter sequences, which is great for efficiency. Or Squeeze Excite, which is kind of this interesting animal. It gets you much better performance in ResNets, but it makes the model bigger, so it can lead to memory issues and it slows down inference. So it's actually a trade-off there in terms of Squeeze Excite. We don't include Squeeze Excite on some of our top benchmarks because the one golden rule I've had at Mosaic so far is don't make inference worse. I don't want people to have to say, well, you made training more efficient, but I have to trade off inference. I want people to be able to say, Mosaic is just strictly better. Using Composer is strictly better. These methods don't hurt me. They only help me. No side effects, or at least no side effects in inference. So Squeeze Excite is great. It's kind of a basic form of attention between channels of a convolutional network. That's the way that I think about this. And so those kinds of methods are tricky because if you modify the network, you're getting into this tricky territory where you may change the cost of inference. Blurpool, another example, which uses anti-aliasing on downsampling. Same idea. Thankfully, slowdown for Blurpool is very small. For Squeeze Excite, there's an appreciable slowdown, but it's so helpful training becomes faster. Inference, that's a trade-off.
One other thing I'm curious about is, say you're trying to maximize how much model/gradient you can fit on one GPU. Is that is gradient checkpointing the best way of doing that right now?
Yeah, I think so. So we have DeepSpeed integration, so we can use DeepSpeed 0, which does gradient offloading. So it'll actually, or activation offloading. So it'll send activations off of the GPU onto the CPU and then pull them back in so that you can basically cram an arbitrarily large model into your GPU memory if you'd like to. So we have integration with DeepSpeed, I think 0.1 and 0.2. So, you can go ahead and use those today. Our friends at DeepSpeed have been really helpful to us. Again, this is the nice thing about being a new layer in the stack. You can kind of collaborate with everyone. I can pretend I'm still an academic because, I like to think we don't really have any competitors, just friends. So, DeepSpeed is available and you can do this. It does cost you something, but that something can be worth it if you're able to cram a bigger model on there.
Yeah, so also on the friends topic, I really love when I was looking through the Composer examples, the integration with HuggingFace and how HuggingFace has done so much abstraction on the model code layer that it's like as much as auto model for language modeling, auto model for sequence classification, is how easily you can interface these pre-trained weights, and all the complexity behind the model definition code is completely abstracted away, and you just point at the task. Can you tell me a little more about the integration between Composer and then Hugging Face? Is just like it does the model surgery, super interesting, and then it just has like a new training layer to it.
Yeah, so what we're really doing is you can bring in your model. Pick your favorite model and just bring it into Composer, and you can use it with our methods in our trainer. In fact, there are two levels to this. One is that for all of our methods, or for most of our methods at least, we have what we call the functional API, which is where you can use these methods in any trainer you want, in any training loop. You want to take these to PyTorch Lightning? Go ahead. Now, there's a reason we built Composer. We built Composer because it's really hard to deal with some of these methods and get them to intervene at the right times. You need a lot of if statements in your training loop if you want to do this right. And there wasn't really a framework out there that provided the faculties we needed. By inventing a new level of the stack, we needed hooks and tools that nobody had really conceptualized before because, nobody had thought about this use case before. So we needed to design a trainer for that reason. And, we started off in PyTorch Lightning, but it really didn't have the capabilities we needed to actually integrate all these methods. And, getting back to that composition of methods question, the reason why we call it Composer, getting all the methods to interleave properly and run at the right times, if you want to use more than like two methods, is incredibly difficult if you're doing it in your own code. So Composer takes care of all that work for you. Each method we have events that happen at different points of the training loop. Each method, can get triggered by events at different times. It can modify the state of the training loop. We make sure all the methods interleave in the right order. If, there's one operation where all the methods go in, we basically have a stack. The first method in is the last method out because, methods need to clean up when they're done. And those sorts of details are really, really hard to replicate in a place like PyTorch Lightning. I'd say we took a lot of inspiration from our friends at FastAI. We really owe them an enormous debt of gratitude, not only for the inspiration on a lot of the ideas that we're using, but also on the inspiration for the trainer, where we use two-way callbacks, where the callbacks can modify the training state. So our training loop is very clean, and then you write these callback functions that can take root at any time during the training process based on these events and can modify the training state. That allows you to inject arbitrary code into your training loop without getting this wildly complicated training loop full of if statements. So again, thank you to our friends at FastAI. We really owe them in that respect. But you can bring your own model to Composer if you want to. And, HuggingFace has a bunch of fantastic models. We're not going to redo that work. That's, great work that our friends at HuggingFace did. And, people already use those models. We use those models. So we had integration for that. Our friend Ross Whiteman, who produces the TIM library of computer vision models, we have integration there as well. So you can bring in your model from TIM and use that. We're working on integration with several other model zoos that are out there because, quite frankly, we don't want to build these models from scratch. That's not our core competency. That's not what we should be doing anyway. And even if we did, you'll want to use the model that's industrial strength already. You wouldn't want to use our Composer version. So, we have them there if you want to use them. We have some basic models we built in, or bring your own. And, our methods should be compatible. And if they're not, it's pretty easy to modify the model surgery to fit the new model that you brought in if, the layers have different names or what have you.
It's such a fascinating engineering design, and the two-way callbacks, the way it lets you interface with these different things. One other thing I'm still kind of trying to piece together with my own knowledge is how the data augmentation flows with it, how you have, say, the data loader, and then, because usually I kind of think of it as like import your data set, define how you're going to be sampling batches from it, define your model code, and then the optimization logic. So how do you kind of tie together that optimization logic with the data loading part?
So we use the standard PyTorch data loader right now, and we're working. One of the big things that we've been working on a lot is streaming data loading, because at the end of the day, you don't want to have to keep your data locally, especially for big data sets. And so we want to make sure that experience is seamless. We're using the web dataset project, and we'll be moving to the new PyTorch data loader that's coming out soon. But with respect to the data augmentations, this is a part of the pipeline I'm less familiar with. But my understanding is we have, it's just another event. Is that, on the data loading, we can, run an augmentation at that point. It's just another place in the pipeline to intervene. So it's just another place where a callback can show up and modify the data.
Can you tell me a little bit more about how you think about which operations happen on the CPU and which operations happen on the GPU? Because
this is a messy question. So this is less of a problem for NLP, where the data is smaller and you don't really augment the data typically. This is actually a pretty big problem for computer vision, where we do a lot of data augmentation, especially in these modern self-supervised models where we actually do a crazy amount of data augmentation, much more than we would do in a standard supervised vision setting. The problem with data augmentation is you got to run it somewhere, and it takes compute to run these image transformations. You have two choices. You can either run them on the CPU using standard libraries, or you can run them on the GPU using NVIDIA DALI. If you run them on the GPU, you're giving up some of your GPU throughput. And in our experiments, you gave up 10 or 15% of your A100 to do data augmentation there, which didn't end up being worth it for us. On the other hand, if you run it on the CPU, you can end up bottlenecked on the CPU. It can take you so long to do the data augmentation on the CPU that you're actually not using your GPU fully. Your GPU is way more expensive than your CPU, so you never want to be in that situation. And what we found is that there are a lot of really interesting papers out there that use, these kinds of crazy data augmentation methods, and advertise like, you can train in fewer steps. Yes, but you're bottlenecked on CPU. Even, the A100s on AWS are very close to CPU bottlenecked on ResNet 50 on ImageNet as it stands, because the A100s are so fast. And quite frankly, Amazon selected a pretty crappy CPU to go with them, all things considered. On our own internal cluster, which, stay tuned on whether other people might be able to access that at some point soon. We picked CPUs specifically for this purpose to make sure that they were powerful enough to keep up with augmentation. So the problem here is that, our best number, ResNet 101 at about 3.5x speed up on those AWS A100s, that is Dataloader bottlenecked. That is actually bottlenecked on CPU data augmentation. We could go faster. We've broken AWS's assumptions about the nature of the instance they should build in the workload by speeding things up so much on the GPU that now the CPU has become the bottleneck. And now we're working with our friends at MIT who wrote the FFCV library to get that integrated, because that's a way of basically doing a lot lower level operations in the CPU to speed things up. And we'll have that integrated. I think it's actually already integrated on CFAR 10 and should be up on ImageNet soon, which should alleviate that bottleneck. And you'll see all our numbers on ImageNet go up a bunch more by virtue of that. So you really got to think whole system on this stuff.
That's so interesting. And I see that as a lot of these methods, I think they have to do some kind of offline style computation. Like maybe it's an exponential moving average of the weights, and it has that kind of background computation of doing the exponential moving average or the stochastic weight averaging. Similarly, I think the SAM sharpness aware minimize, I think it also has some kind of optimization computation it does. What do you, sorry.
Oh, yeah. For SAM, you have to basically do the backward propagation step twice, which can get pretty expensive.
So I'm also really curious if you think about these like pretty kind of ambitious meta learning loops where you have sort of like a teacher student, you have like a teacher inference. So maybe things like meta pseudo, or even maybe kind of coming more into the things that are already in Composer. We have Augmix, where Augmix has, what Augmix is, for people who don't know, is you take your original image, you form 3 augmented versions of it by randomly sampling 3 configurations from randaugment, then you do a pixel-wise averaging of that to get the final augmented image. And the next extension they did was Augmax, where they add an adversarial controller into the weighting of those 3 pixel-wise averages. So you're starting to add more kind of optimization in these little things. How do you see that kind of idea of adding optimization, not just in the gradients of the classifier, but also in, say, those kind of meta layers of these kind of algorithms playing into the Composer design as well?
I think it starts to necessitate a different computational architecture at that point, because the augmentation step has gotten so expensive. So we don't use Augmix. We have it implemented. Augmix, we have found no scenario where we can get around that CPU bottleneck for Augmix. You have to do 9 image augmentations. Your CPU bottlenecked across the board. Randaugment, we found, works decently if you have a good enough CPU to GPU ratio. That can either mean you slow things down on the GPU, you use methods that make things slower but reduce the number of steps, or again, it's a balancing act. We got to make sure that our GPU and CPU throughput are balanced, or you just use a bigger model, which takes longer to train, or you have a better CPU like we have in our own internal cluster that that allows you to use randaugment productively. Another interesting scenario where this starts to help, if you look at the AWS T4s, not the A100s, but the T4s, they're pretty wimpy GPUs. They're built for inference, so they're about a third as fast as a V100. But AWS way over provisioned the CPUs. So actually on a T4, you can use Augmix and randaugment just fine. So in fact, in scenarios where you want to do a ton of augmentation and you don't really care about how long the job takes, just cost, the T4s may actually be a much better bet than the V100s or A100s. But augmix, we haven't really found any other scenarios where it makes sense. Rand augment, it makes sense in certain scenarios, especially for long training runs. But by and large, Matthew Levitt, who implemented these methods for us, I think was pretty frustrated at the end of the day that they didn't make sense simply because they were slowing down each step, and they were taking, the bottleneck was no longer on our most expensive component on our GPU, it was on the CPU. So, great methods, very useful. But when I look at some of these self-supervised learning papers and I see the amount of augmentation they're doing, I kind of take a step back and go, I wonder if they're fully utilizing their GPU. But in terms of how to do this going forward, or you start to get into these adversarial scenarios, you need an accelerator just to do your augmentation. And I think NVIDIA, I haven't looked too much at the H100 setup. If I recall correctly, they have kind of this co-processor H100 that does networking, data loading, and preparation to send it to the real A100s or the real H100s. So, I think NVIDIA's gotten the memo that having these co-processors is necessary. You need a GPU just to prepare your workload for your GPU. Then you get into questions of, is that the best use of your resources, or should you just drop it all together? That's a complex systems optimization problem, but this really changes the architecture. And I will say that makes a lot of sense for vision. I think it makes less sense for NLP, where data is just smaller in terms of number of bytes, and we don't do data augmentation. So this does beg the question, do you need two different hardware setups for vision and for NLP, which complicates the hell out of everything?
Yeah, and I think maybe in NLP too, you don't really probably repeat through your training data as much. Like if you're going through like web text, you probably will never even make it through the whole data set with most of the training. So it's like, why augment it to begin with? And maybe just quickly, I wanted to see what you think about maybe like offline data augmentation, where you kind of start storing. So it's not stochastic anymore; it's deterministic, and you store the augmented data set. There's a paper called the Deep Bootstrap Framework, where they sample from a DDPM generative model, and they store the data set. It's CFAR 5 million. It's available on GitHub, so you can you have this offline. In that case, it's sampled from a generative model, but you can imagine applying rand augment and then storing it. Do you think that would be a useful direction going forward?
I think the data sets end up getting too big. For ImageNet, you're repeating through the data set, let's say 90 times conservatively. That used to be the standard back in 2015. In the past couple of years, I've seen this creep upward to 180 and then to 300 and then to 600 times through the data set. ImageNet is already uncompressed, probably about 400 gigabytes, I'm guessing. Now you have to do that 100 times over, and you're talking, what is that, 40 terabytes of data? So then you get into questions of, is it worth the storage costs, and is it worth the network bandwidth costs to stream this data, over your cluster? That can become its own issue, especially if you're streaming the data from, one cloud region to another, or from one part of the cloud to another. Usually for data sets like ImageNet, you can cache them locally, or at least they automatically get cached in memory if you have about a terabyte of memory. You obviously can't do that for a data set of this size. So I think this can work for CFAR. Once you get beyond CFAR, I don't think it makes a ton of sense. And really, at the end of the day, you start thinking, in terms of storage costs, it's cheaper to have a co-processor that will do augmentation, or to just buy some really big CPUs than it is to pay for that extra storage.
So one more idea I want to run by
definitely.
you before coming back to the efficient machine learning is, what if maybe we stored the vector representations of ImageNet? So we had something like some kind of API offering that produces vectors, and then we store those vectors, and then we start having complex networks from vector representations. Or maybe it could be like the VQVAE, where it's still like a matrix, but it's like, how they map it into the discrete codes, but some kind of compressed representation. And maybe we could have storage and things like a vector database that would store those things.
No, I think this is a great idea, and in some sense, that's almost where we are as a community. You can think of SimClear and Moco, or whatever the latest greatest method is. You can tell them a year out of date on this topic. That is what we're getting essentially. Is if we were to just train a network on top of those vector representations, that's what you do when you fine tune SimClear or Moco, assuming you're just fine tuning the head and not the actual network. If you fine tune the network, obviously it's more complicated. One of the biggest challenges there is, again, augmentation wise, you've got to actually perform all this augmentation at some point. But I guess to your point, if we have a smaller representation of the image, then we can do all that augmentation offline. And I've also always wondered, I'm sure someone's written a paper about this, can you find, ways of basically doing an augmentation to a vector that is equivalent to an augmentation, of the image itself, and so that you don't even have to store the image. So I think this is yet another place where these vector style representations are incredibly valuable. So I'm all ears on that. The biggest challenge is still, you've got to get that SimClear or Moco style network. And what I'm finding and chatting with a lot of folks in the community is they want to train their own network on their data because they have a huge amount of data. self-supervised learning unlocks this gigantic amount of data that most companies and just many individuals have floating around. And nobody wants to use GPT. They all want their own GPT. Nobody wants to use a pre-trained SimClear Moco. They all want their own. And, people often ask me if, we only do few shot or zero shot learning, what's the point of training? What's the point of Mosaic if people are using, these vector representations and that's it? My response is, so far, I have seen no evidence that people are training less. The H100 would not be coming out if people were training less. So as far as I'm concerned, as long as there's training, there's Mosaic, and people seem hungry to have their own BERT model pre-trained on their own task, or fine-tuned, quote unquote, on their own data, but they have more data than the BERT was pre-trained on to begin with anyway. So rumors of the death of training have been greatly exaggerated. I'll say that much.
Yeah, I think that's one of the most fascinating topics in our current stage of deep learning is this, can we just use prompting where we just have these maybe discrete prompts or predefined templates to get large language models to do whatever we want trained on infinite data? But even then you would have like a continuous prompt tuning usually where you put the prompt into a latent space and you still want to put gradients through it. And those papers seem to be the ones that are more successful anyways. And so and then quickly before coming back to prompting, and then the idea of, like one model produce, and in vector search, when we talk about embedding APIs, it's like, can one embedding API produce embeddings for every kind of application, whether it's e-commerce, biomedical literature mining, news reviews? And it's like, there's a paper called Don't Stop Pre-Training, which shows that, that's not really the case.
Yep.
Fine tuning on the domain is going to be useful. So coming back to prompting and this idea of still putting gradients through continuous things that you put in the middle of the networks, what do you think about, and there's papers like VNL adapter where they only fine tune 4% of clip. They don't fine tune the whole architecture. What do you think about that kind of masking in the architectures to, put these little layers that you update?
I think this is a great idea. I've seen this, I wrote this paper on training only batch norm, where I started with a randomly initialized network. And thought it was cool that you could still get good performance just by training the batch norm parameters, which, for reference, they're not really real parameters. They're kind of scaling factors and bias factors for random features in the network. I thought it was cool that you can train even okay with this, let alone train somewhat decently. I won't claim you can train well. That's a bridge too far for that paper. But, in writing that paper, I discovered this is an old idea. Most people aren't starting with randomly initialized networks, but there's this great paper called K for the Price of One that shows, okay, you just, create new sets of batch norm parameters for each downstream task and keep all the other weights fixed. So I think this is a pretty profound idea. And it's a nice spin on the idea that we've always had of transfer learning where you just replace the head of the network and keep everything else. It looks like the right answer is actually, having trainable features scattered throughout the network is the way to go. So, I think this is a deep, profound idea. The biggest challenge being as soon as you scatter these parameters, it's not as efficient as just training the head because you have to, forward prop and back prop through all these other layers in the network. There's a cost to doing this, but, given how much better it works, I'm sold. I think this is a fantastic idea. I won't give credit to any one person for this idea because, I'm sure this idea goes back into the 80s and before if we really were to dig and find evidence of it, just as all good ideas in deep learning do. But it's an idea that seems to keep coming back, and there's a reason it keeps coming back.
Yeah, that paper, training batch norm and only batch norm, that just was like, how can that work? Similar to things like layer sharing. I can't believe layer sharing works either. These things that kind of defy sort of like my core principles of how these kind of things work. And so, mentioning that, you still have to kind of train this whole thing. And so, is that kind of still what's bottlenecking, bringing all the way of the sparse subnetwork masking back to life, kind of?
Not really. I think I'm guessing if you were to sit down with a couple folks from industry, and I have no insider knowledge on this, I'd guess that you'd hear that if folks have kind of a multitask setting, they're using this. Especially, I'm guessing on mobile devices, things like this are in use. It's a great way to efficiently store many different networks in a small amount of storage. So I would hypothesize to you that this may be running on your phone or your computer right now and you just don't know it. And I don't know it right now. So it's a good enough idea. I'm sure it's in practical use.
Do you
There's
like
someone in the bowels of Google somewhere who's doing it?
Do you like these mixture of experts models? Do those kind of things excite you?
They do excite me. I think they excite me for a couple of reasons. One is that, it's a way to train bigger models without increasing the cost of inference. You're kind of, you get more parameters for free in some sense. It's not quite free. You have to manage all these experts and you have to use the right ones at the right times. But assuming, ideal costs and not thinking too much about how do you load the right experts at the right times and all that good stuff, it's basically keeping the cost of inference fixed as you increase the parameter count. That's a huge, brilliant idea. And the other piece is, it's sparsity. I like sparsity. And, that's what I'm known for. Sparsity shows up in all different forms in neural networks. And as I mentioned, weight sparsity, which I've studied, probably, I would say it's the most interesting part scientifically, but one of the least useful parts of sparsity. Mixture of experts is really interesting to me scientifically, but more importantly, it's incredibly useful practically. So I'm a believer. I think the biggest challenge with mixture of experts is there's some threshold you cross where you need a sufficiently large network before mixture of experts starts to make sense. And the question we should ask ourselves is that threshold going to increase over time or decrease over time? Will we get better at training non-mixture of expert models to the point where, really, mixture of experts aren't useful until 100 billion parameters, aren't useful until a trillion parameters? Or actually, are mixture of experts going to scale down to the point where they start being useful all the way down? I think this is a big question for us as a field. I'll point to one trend as context for this. I look at vision transformers. This is something that, I still train ResNets. I'm still a believer in convolutional networks. Vision transformers are popular, and I think they're really exciting. There have been a bunch of papers in the past few months showing that actually if we just give all the ResNets the same tricks we gave to vision transformers, we can, ResNets work to larger and larger scales than we would expect otherwise and do better and better. The threshold where it makes sense to switch from a ResNet to a vision transformer is getting higher. And, if that trend continues, I kind of wonder, will vision transformers always be niche to some extent because we'll keep getting better and better at training our CNNs? I'm not entirely sure, but it's always a question to watch. Where do those thresholds go? Do they go up, in which case CNNs may be the future? Do they go down, in which case vision transformers may take over? Same thing for mixture of experts. Does that threshold go down, and do we have small mixture of experts that are more useful than the equivalent small models, or do we get better and better about training those, quote unquote, small models, as in smaller than 10 billion parameters, to the point where mixture of experts, only make sense at the absolute largest scales? Open question, but always worth keeping those trends in mind.
Yeah, that's fascinating. The idea of bringing the mixture of experts down. I mean, it kind of seems like the sparse subnetworks idea. It's very similar to it, right? In kind of the purest form of it. And so I kind of did want to ask you a little more about attention and convolution, just quickly. I've really been liking attention for, say, like feature like latent space fusion, and particularly with like multimodal image text models, where you kind of compress it in a bottleneck all the way such that you have a vector representation of the image, you have a vector representation for the text, and obviously we like to search through the vectors with our dot product. But then when you want to fuse that, you can have that attention. Do you like that kind of attention layer for that thing? And when you think about generalizing it, do you think convolutions, maybe like an MLP layer to fuse them, or you could just concatenate them along the? I think with some computer vision architectures, you just kind of concatenate a tensor of features along the channel axis and then just convolve away with it, right?
So I think I'll give you the boring answer, which is what I like has nothing to do with it. At the end of the day, it's what works. And I'm a believer in the science, and we should do the science and understand what works best for application. We should look at the trade-offs in performance. I don't have enough experience with multimodal models to tell you what the right answer is. I will say CNNs are still pretty darn good for basic computer vision tasks. But when it comes time to combine features from multiple different representations or multiple different kinds of features from different kinds of backbone networks, it would surprise me if convolutions worked well in that setting, because really they are a great fit for dealing with image activation maps and not so much for dealing with arbitrary tensors. Although there were a lot of CNN-based NLP models in the pre-transformer days. So I would expect that attention or a feed-forward layer would work better. As to which one and in what context, I leave that up to you to go and do the research and find out for yourself, and report back to me and let me know. I know there's been a lot of push back and forth of like mixer models and, just kind of non-attention, but attention looking, not attention transformer style models versus attentive models. At the end of the day, we can do the science and find out for ourselves. And, I like whatever works best. You do the work, let me know.
That's a great answer. Transitioning into what I wanted to ask you next is, you have such a clear thinking about asking scientific questions. I really admire that. I think the way that you're able to pose these questions, identify the interventions, confounders that are in these experiments is a very profound skill. And I wanted to ask you how your experience has been with your science and then starting a startup. How has the science and the startup creation played together?
The startup will not succeed as a business unless we do good science. And that is somewhat by design. You know, I don't want, we have a big research team at Mosaic. It's about a third of the company right now. And it will, you know, it may not always be that large because we got to build a business, but it will still be a significant research team and it's going to grow. The company will grow faster than the research team. You know, the research team may be growing by 50% or more by the end of the year. Also, you know, mosaicml.com/jobs. Come apply for a job. We're growing. But I don't want us to be a Google Brain or a Fair where this is a fun diversion for an executive who's already made all their money and just wants to do something interesting. You know, no pointing fingers, but I want to make sure that we're doing science that is essential to the business. To get these speed up methods to work well, we have to intervene into training very carefully and we have to understand what we're doing and why. The why makes us more efficient in terms of developing these speed up methods. The why is good for the business. We are certainly in this wonderful scenario right now at Mosaic where the science and the business are aligned. We can't have one without the other. And so we have to do great science. We have to be rigorous. We have to turn over every leaf. We have to be even more rigorous, I would argue, than you have to be in academia because we're not just trying to sneak some graphs through the publication process and, you know, sneak some claims through. This has to actually work. And it's, you know, anybody who's written a paper knows going from getting a graph in a paper published to getting it to actually work is really hard and really scary. And often we say, we'll leave that to the practitioners. Well, here we are, we're the practitioners and also the scientists, and we have to make this happen. So, you know, I think the science we're doing at Mosaic is as good, if not better, than the kind of science that would be done in academia. And it's impacting the real world, so that makes it all the more difficult. I will also say when it comes to scientific communication, as I mentioned before, you know, we need to basically put prescription labels on each of these methods and describe everything about them. It looks like you've seen our method cards, which our researchers worked really hard on, and I spent most of the past month on just revising and cleaning up all of them to tell you, how does this work? What does it do? What are the trade-offs? What are the warnings associated with this? What side effects might it have? Because you need to know. You won't trust me to say, like, I did something crazy to your model and I won't tell you what it is. We have to earn your trust. And so we have to communicate all of this information. A publication is not the most efficient way to do so, but scientific communication is still paramount for our research team. So as far as I'm concerned, science and business completely aligned. And I'm really grateful for that kind of opportunity because, you know, I think it gives the researcher so much more of a sense of meaning than you'd have if you were just writing papers all day.
Yeah, that's so interesting to hear, and yeah, the startup and the science, the way it plays, is so interesting. And I did want to quickly come back to I love the mention of the interaction effect between these different methods. When you mentioned that at the beginning of the podcast, it was just like mind blown for me thinking about that. Do you see that as the way that you're going to empirically collect these data set, the experiments to see how does stochastic depth mix with augmix, and how does ghost batch normalization interact with some kind of other strong regularization, such that your overregularization is going to be, you know, ruining the training? Is this kind of similar to hyperparameter tuning, where you might use things like maybe ASHA, where you have different resource allocation, these kind of strategies to test all these configurations? How do you plan on exploring the combinatorics of that space?
It's sort of like hyperparameter tuning, except that, you know, I'm not sure the space has the nice smooth shapes that you want for hyperparameter tuning, where, you know, as you increase the learning rate, accuracy gets better and then worse, for example. I don't think the space necessarily has those dynamics, because adding a method or not adding a method is a discrete transformation. In a lot of cases, you can't just kind of slowly phase in a method in a way that would make hyperparameter tuning work much better. And, you know, these methods, again, have these weird, crazy interactions that are, you know, not smooth in the way that hyperparameter tuning would expect. So really, I think the way that we're going to do this is a couple of ways. One is we're getting intuitions for the way that these methods might interact, for how you know, I mentioned before, balancing the training process. If I've got something that, you know, requires extra augmentation on the CPU, I want something that will actually slow down each step on the GPU. Ideally, that is traded off for training for fewer steps, something, again, like SAM, like sharpness aware minimization. But SAM, if it can reduce the number of steps and not slow things down too much, that can make room for a better augmentation technique, and you hit this virtuous cycle. So it's a systems optimization question in that respect. There are also things like the regularization budget, where, you know, we have a lot of different regularization methods we could use. We should use the ones that basically impose the least overhead for the best improvement in accuracy. We developed this method in-house called callout. It's a lot like cutout, which is where you take an image and just cover up a square patch of it, except instead of covering up a square patch, we eliminate rows and columns from the image so that you can actually lower the resolution. It's like cutout, but faster, because now you actually can take advantage of those missing pixels. So these are the sorts of tricks that, you know, come in handy. And these are the ways of thinking about it. But there's a science here, and by improving that science, we'll get better about coming up with these recipes, not only ourselves, but ideally automatically for customers. And then on top of that, once we have a good recipe for a particular vertical, like say ResNet 50 on ImageNet, our hypothesis is this should work reasonably well for other related models like DenseNet or for other image classification tasks. So there's a way of kind of taking advantage of all of this. But it's right now it is more alchemy than science, and we're trying to develop a science in a completely new area. For the record, I think this is a great academic problem, and I would encourage folks in the academic world. This is one of several big, new, exciting academic problems I wish people were working on right now that I've discovered only through kind of being pressed into the real world and having to deal with some of these constraints that I can usually avoid as an academic.
And so it's super interesting. I mean, the idea of lowering the resolution, all these efficiency gains in general, maybe can enable, say, video processing, where we've been bottlenecked by having to have these absolutely massive data sets to try to have high resolution, high frames per second video. But really what I wanted to ask you about next is, have you been how have you grasped your intuition with the deep double descent phenomenon and things like Grokking, where they show that they leave it running? I think they even say that their experiment, they had just left it running accidentally. And what happened is it was like overfitted. Then like 2 days later, suddenly it like has learned generalizable representation somehow. How do you wrap your understanding around double descent and these kind of things?
Double descent bends my mind a little bit. There's a paper that I'm working on with a student in my old research group where we're looking at the relationship between sparsity and double descent to try to understand maybe is the double descent phenomenon really just having a lot of parameters means you find a small subset of parameters that actually work well, and it just gives you more options, but you're still learning a low dimensional representation. So this is something we're talking about and thinking about. To some extent, the double descent phenomenon doesn't really matter in practice, and I'll go out on a limb and say that for a few reasons. First of all, we're often not training these models to the point where they can memorize the data. Often the models cannot memorize the data. GPT-3 can't memorize the training set. It's nowhere near big enough. ResNet 50 can't memorize ImageNet. It's not big enough. So, on that hand, we're not really in that regime necessarily. Double descent is maybe an exaggeration of a regime. The other part is that in order to get those two descents, in order to get like that sharp peak in between, you have to work for it. You have to, like the deep double descent paper had to use random labels to get that to show up. That wasn't something that just shows up naturally. It looks almost like a smooth curve with kind of maybe a little bend in it, but you wouldn't really tell this phenomenon is happening. So it does, I think, beg the question, coming back to where I started at the beginning of this conversation, to what extent is this a natural phenomenon, and to what extent is this an artificial phenomenon that we can suss out to use to understand what happens naturally? But there's always that question of, when you see an artificial phenomenon, how much does it have to do with practice, and how much does it have to do with the natural world? I think deep double descent does have a lot to do with the natural world. Perhaps I don't understand why yet, and we don't understand why yet. But it's always worth asking that question: how well does our model, or how well does our setting of inquiry actually relate to the settings we care about? And in deep double descent, I think we've oversold a little bit just how natural these settings are. They're not that natural at the moment.
That's an eye-opening takeaway from me, because I've just come to accept deep double descent as something to be aware of, but I actually haven't really encountered it in the experiments I've been running. It hasn't really been something that has come up with me. But so the next topic then I'm super excited to get into is, I see MosaicML as almost being like electric cars, in the way that this is going to help with climate science and, say, the damage that is done by training things like GPT-3. And if we just continue this arms race of just run as much as you can to build your AI businesses, compared to these kind of efficiency algorithms which are reducing that kind of footprint on this. Can you tell us about your mission on helping with climate science with these algorithms?
Yeah, so a big part of at least my personal motivation here is the energy usage aspect. Just as these models cost a lot to train and they take a lot of time to train, time is money and time is CO2. Now, we haven't looked into CO2 emissions that much at Mosaic, simply because I recognize it's easy to do a bad job of CO2 emissions calculations. These data centers are often using renewable energy or near energy sources that are less CO2 intensive. These data centers may use different mixes at different times of the day. So the amount of nuance you need to be able to tell people, yes, using these methods reduced your CO2 emissions, is actually really difficult. And this is the scientist in me. I don't want to do it unless I can do it right. So if there's someone out there who has expertise in this topic or is excited about looking to work on this, I want to hire someone to basically spearhead this. But I know I'm not the expert, and I'm not going to read a couple papers and become the expert. Someone has to have studied this for a long time to really know exactly what to do here. So, I don't want to do this until we can do it right. But by that same token, just if you look at sheer energy usage, time is money and time is energy. And we know that at least from an energy usage perspective, if you can train more efficiently, you can reduce the energy usage. And I look at the H100s, I had a rather cynical tweet yesterday that I will try to explain, which is, the H100s are pretty remarkable. They're 6x faster, at least if you look at the SXM highest bin part, one that we probably won't see for another year. But, 2x of that is from floating point 8. So kind of, a little bit of cheating in some sense. As you start working your way down, that 2.5x or 3x faster that you get is by doubling the power. You're going from 350 or 400 watts to 700 watts on the SXM parts on the highest end. Moore's law is dead. Dennard scaling is dead. The idea that every 2 years you get a new part that is the same cost as it was before, but is twice as fast for the same energy, that's dead. We got a new part for twice the energy that is about 3 times as fast. And, jury's out on the price, but I expect it'll be pretty expensive at first. So, plot that trend out. And, maybe the next part we get will be 2x the power, 2x the price, and 2x the speed. I don't know how much further we can keep pushing this without throwing more power at the problem. And so we've just hit our limits. The models are getting bigger. What is it? The stat is like 4x per year larger in the past couple of years. Hardware has gotten, let's see, we've got 2 years. We doubled our power output, and we, 2.5x or 3x our compute. So 50% improvement over 2 years. Call it 25% per year. 25% per year in terms of hardware efficiency per watt, and probably efficiency per dollar. 4x or 400% increase in model sizes and model flops. You can do the math and see there's a pretty huge gap there. And we just need more compute and more power to keep up with these models. It's not like the good old days of the 90s or the 2000s where, what was the saying? Intel makes and then Microsoft takes. Intel doubles the amount of compute per dollar. Microsoft makes the software twice as resource consuming. We're not in those days anymore. We're just consuming resources way faster than we can keep up with it. And hardware is not going to do it. All the fancy architectures in the world that folks are coming up with are very exciting. NVIDIA is still the fastest, most efficient chip in town, despite all the interesting hardware architectures coming out from startups. And you can see what's happening to NVIDIA. So what's going to close that gap? Either it's just going to be out of reach, incredibly expensive, and incredibly bad for the world, or we have to change the algorithm. That's where I think Mosaic comes in. I think this is the future of how we're going to be able to take that 400% increase per year and make sure that it's at the same cost.
And I think that was one of the comments on your tweet was if you have it, people are just going to run twice as many hyperparameter configurations.
They might. At the end of the day, people will spend their budgets, but budgets are not going to increase 400% per year. So we can talk about energy, we can talk about time, but let's focus on cost. At the end of the day, somebody's going to say, you need to spend how much money to train this model? You spent 4 times less last year. What are you talking about? And if budgets don't scale, that's the end of the day. If people want to use their budgets to do more, if people get their budgets 4x and want to do hyperparameter tuning, to some extent, more power to them. I can't stop them. And, Mosaic will do better as a business if they decide to do that. But, I like to hope at least, at some point, some executive is going to say, what the hell are you doing? Why are you spending all of our money training this one model? And at that point, we're going to have to do something different.
Super cool. Well, Jonathan, thank you so much for your time and for coming on the podcast and discussing all these just amazing things. I think the work that you're doing at MosaicML, everyone out there should really try the Composer. It's such an easy thing to add on to your existing workflows, and testing out these methods is so incredible. So thank you, Jonathan, so much for telling this story.
Thank you so much for having me. I'll give 2 quick shout outs, actually 3 quick shout outs at the very end. One is I'm just the messenger. This is the work of a huge team of researchers, engineers, everybody at Mosaic. So it's really nice that I get to show up and brag about 30 people's worth of work. I really am the manager here. I have not written a line of code since I got to Mosaic. So credit where credit is due to the incredible team. And I'll say, if you want to join that incredible team, we are hiring like crazy. So mosaicml.com/jobs. And the last thing I'll say is, check out Composer, give it a star. I promised everyone that, I'd try to get us to 1,000 stars by the end of March, and the end of March is coming up. So, a star would be great. Composer.dev, you can take a look. Thank you so much for having me.
Thank you. And the Composer, to give it a star, will be linked in the description of the video. First thing, so go click that and do that right now.
Thank you so much. Take care.